Okay, good evening, everybody, and welcome to another online session in organic chemistry. Before we start the session, I would like to call on Natalia. Natalia, why are we here this evening?
We're here for a review for the exam 3, and this review, we're going to deal with carboxylic acids and nitriles, carboxylic acid derivatives, and Enolate anions chemistry.
Okay, thank you. So for today, we are going to review for the third exam, just as Natalia had just informed us. And for this session, we will be discussing the chemistry of carboxylic acid and nitriles, which is taken from chapter 20 of your book. We are also going to discuss the chemistry of carboxylic acid derivatives, which is from chapter 21 of your book. And also, we are going to discuss the Enolate anion chemistry, which is taken from chapter 22 of your book. But before we start, let me go ahead and acknowledge those of you who already joined us. I see Ebra Jipo, Cynthia Jaffor, Ines Kifando, Jaconda Kepas, Kiera Bradley, Natalia Stepanova, Pravin Cheka, and Rahul Sharma. You are all welcome. So at this point, let us go to the first question. By the way, we are going to use questions from a previous exam that was given in spring of 2012. I hope you guys have a copy of that exam with you. So what I want you to do, to go ahead and send me a text as to what preference do you have in terms of those questions on that exam, if you have any preference. Okay. Okay, if you do not have any preference, okay, so let me go ahead and start with question number 3. Okay, Jaconda, can you go ahead and read this question for us?
Provide the missing reagents in the following synthetic scheme.
Okay, thank you, and very good. Okay, so what we need to do here, we need to provide the missing reagents in the following synthetic scheme. Of course, this should be a review to all of you. So I am hoping that this will be an opportunity for you guys to refresh your knowledge on the reagents and reactions. Okay, so let us take a look at this one here. A. We are going from this molecule here, which is a beta keto ester, and then we have to make this here. Okay, so what reagent do we need? Okay, in order to answer that question, of course, we know that we are introducing a methyl group. So this is an alkylation reaction. So what reagent do we need? Okay, you guys said sodium methoxide followed by methyl bromide. Okay, somebody said LDA followed by methyl bromide. Yes, you are all correct. Excellent, excellent. So let us do this right here. So what we need here, we need step 1, LDA, which is lithium diisopropyl amine, and then we follow that up with an alkylating agent. In this case, we use a methyl bromide. Okay, this is going to be an SN2 reaction. Essentially, the LDA will form an Enolate anion right here, because this hydrogen here is a lot more acidic than this hydrogen here. So once we form the Enolate anion, then there will be an SN2 reaction, a displacement of the bromide, Now then we then do the alkylation right here. Attach the methyl group to this alpha carbon right here. Okay, so very good. About the next one, B. What is the answer to B? What are we doing here? We are going from this beta keto ester, and then we are going to lose this group right here. And so how do we do that? What reagent do we need? Okay, you guys said okay, acid hydrolysis followed by heat. Okay, very good. So you say we need to do this. Okay, use dilute acid with heat. That is correct, because what are we doing here? Okay, in essence, what we are doing here, when you apply the dilute acid here, you will be hydrolyzing the methyl ester to a carboxylic acid. Once you get your carboxylic acid, you apply heat, and then you are going to lose carbon dioxide. Because in this case, you will have a beta keto acid. So this is what you have right here. Okay, so in this case, once you apply heat to this, you lose carbon dioxide. And you form this here. Think of forming an enolate in transit. Plus the proton that is released right here. And then, of course, that proton and the enolate will join together to form the final product. Okay, very good. So now what we need here, the reagent that is needed here is dilute acid, then with heat, and that will do the the reaction that we need. Okay, about C. Okay, what do we need here? Okay, somebody's asking a question here. Oh, okay, I got you. Christopher, okay, I see you. Very good. Okay, for C, okay, what are we doing? In this case, we are going to do another alkylation. In this case, the alkylation will be on this carbon here. We are going to alkylate this carbon. Okay. Take this out of here. Okay, so to do that, you need LDA. You guys said we need LDA. Okay, step 1. And then once again, you follow that always an methyl iodide or methyl bromide as alkylating agent. So we are going to alkylate this carbon right here, because what happens here, the LDA will deprotonate this carbon to form an enolate anion on this carbon. Because some of you may want to ask, why not form enolate ion on this carbon? The reason why not is because of steric hindrance. Because of steric hindrance, the LDA being a bulky group, will prefer to deprotonate this hydrogen here to form the enolate here, and then once the enolate is formed on this carbon, then it undergoes an SN2 reaction with the methyl bromide to form this compound here. Then some of you may want to ask, okay, if that is the case, how come LDA deprotonated this hydrogen here? Some of you may want to ask that question. Okay, the reason why the the reaction took place on this here is because this hydrogen here is a lot more acidic than this hydrogen here. Okay. The pKa for this hydrogen is about 10, whereas the pKa for this hydrogen is about 20. So that's a factor of about 10 to 10. So this is a lot more acidic. Therefore, LDA will prefer to simply deprotonate this to form the enolate ion subsequent to the SN2 reaction. Okay, is there any question on that? Okay, very good. So let us go to the next one. Okay, A. What do we need to do here? What are we doing here? Going from this molecule here to here. What are we doing? Okay, very good, very good. Okay, we are doing hydration. Okay, this is hydration reaction. Okay, what type of hydration is this? Is this a Markovnikov hydration or anti-Markovnikov? Okay, anti-Markovnikov. Very good. Anti-Markovnikov. Okay, in other words, we are going to be adding the elements of water across the carbon-carbon double bond in an anti-Markovnikov fashion, which means that the hydrogen goes here and the hydroxide goes here. Okay, and the reagent that we need, you guys already told us. Very good. You said that we need borane. We need step 1, borane, and step 2, hydrogen peroxide in basic medium. Okay, very good. Okay, now we want to, about this here, B. You want to go from here to here. What do we need? Okay. Okay, we do phosphorus tribromide. Excellent. Excellent. That is good. I know this question will be a piece of cake to all of you because this is simply just knowing your reagents. Okay, so this is PbR3. Okay, PbR3 will transform a primary alcohol to a primary alkyl bromide. Okay, in other words, the bromine will replace the hydroxide. Okay, very good. About C, at this point we want to go from the alkyl bromide to the nitride. Okay, good, great. You guys say KCN. Okay, potassium cyanide, and this will be an SN2 reaction. This will be an SN2 reaction. So the cyanide will be acting as a nucleophile. The cyanide will be acting as a nucleophile, okay, to displace the bromine in an SN2 type reaction. Very good. Okay, about D. Okay, for D, we want to go from the cyanide to the carboxylic acid. Okay, very good. Okay, Jaconda said hydronium ion. Yes, that is correct. Okay, hydrolysis, acid catalyzed hydrolysis of a nitrile will give you a carboxylic acid, and that is what we have here. Okay, so far so good. How about E? Going from a carboxylic acid to a primary alcohol. Excellent. I see the answers already. Okay, you guys say we could use lithium aluminum hydride. Okay, and then follow that always with dilute acid or water. Let's get this out of here. Okay, so you guys say we need to use, for here, we use LAH for lithium aluminum hydride, and then we follow that up with dilute acid. Okay, let me ask you this. Okay, what other reagent? Oh, okay, okay, you have answered the question. Ebra and Praveen said we could also use borane, but when you use borane, you do not follow it up with hydroxide, peroxide, what to do, you follow it up with dilute acid. So you could also, I say, or we could also use step 1, borane, and then step 2, you follow that up with dilute acid. Okay? Okay, very good, very good. Okay, about F, the last step right here, we want to go from a primary alcohol to an aldehyde. Okay, excellent. You guys have PCC, okay, pyridinium chlorochromate. PCC will take a primary alcohol to an aldehyde. Or you also said we could also use desmartin. You could also use desmartin or desmartin iodine. Okay, either PCC or desmartin iodine will transform a primary alcohol to an aldehyde. Excellent, very good. Okay, so let us go to the next question. Is there any question on this before we move on? Okay, somebody say, can we do 7? Okay, let me write those down. You want to do 7, 14, and 10. 7, 14, and 10. Okay, very good. Yes, okay, so let us go straight to 7 then. Okay, a lot of people say, okay, some people say 9. Okay, so we will go by 7, 14, 10, 9, and 8. Okay, we will do 8. Okay, very good. Before we leave, very good. Okay, I'm glad you guys have given me your choices. Okay, so let us go straight to 7. Okay, right now I do not know how many of you have a working mic. If your mic is working, can you go ahead and read this question for us?
Using cyclohexanol, ethyl malonate, and other appropriate reactions and reagents provide a synthetic scheme for the following compounds.
Okay, very good. That's Akira Bradley. Okay. So now what they want us to do here, they say, okay, using cyclohexanone, so we need to know the structure of cyclohexanone. In other words, this here. And then also ethyl malonate. Also, they want us to use ethyl malonate. Okay, so they want us to use cyclohexanone and ethyl malonate and other appropriate reactions and reagents then to provide the synthetic scheme for this compound here. Okay, let us see here. Okay, so let us start. We want to start with, anybody has an idea? What do we need to do? Okay, let me take a look at the starting material, cyclohexanone. Okay, and ethyl malonate. Does anybody have an idea what to do? Okay, you say we want to form the, use a toxide to form the enolate anion. Okay, great. Then somebody say we need to form the alkylating agent. Excellent, excellent. That is, those two answers are correct. Okay, but we need to do the, form the alkylating agent first. That is correct. So, let us see here. How do we form the alkylating agent? If you look at this here, let us do some analysis here. We assume at this point that this carbon here will be this carbon, okay? Okay, therefore, let me number the rest of these carbons here. I say this is carbon 1, this is carbon 2, carbon 3, 4, 5, 6, 7, 8, and 9. Okay. Now, so we have already told you that carbon number 2 will be this carbon, the alpha carbon in the malonic ester. Therefore, the question that I have for you, for the alkylating agent, what carbon would the leaving group be attached to? The leaving group of the alkylating agent, what carbon will it be attached to? Carbon number 3. Excellent. Very good. Okay? So that means, therefore, we need to transform this cyclohexanon to a molecule in which we are going to attach a carbon, form a new carbon-carbon bond right here, replace the oxygen with a carbon atom. So definitely we need to do that. Okay. So therefore, if that is what we need to do, we need to transform this oxygen to a carbon. What reagent will allow us to do that, to form a new carbon-carbon bond? Anybody? Let us start with cyclohexanon. Any suggestion? Any suggestion? Okay, somehow this carbonyl must become, okay, great. You guys said we should use Wittig. Okay, Natalia, Ines, okay, excellent, excellent. Both of you are correct. So we want to use a Wittig reagent. We have a Wittig. We are going to use this Wittig here. This here is 3 phenyl groups attached to our phosphorus. Okay, so once we do that, then we get this. Then you get a carbon-carbon double bond. So at this point, we have replaced the oxygen. So now what is next at this point? Keep in mind, we want to attach a leaving group to this carbon, to carbon number 3, which is this one here. So what is next? Okay, borane, okay, excellent. Okay, okay, so you say we need to do step 1, boration. We want to form a primary alcohol, an anti-Markovnikov addition of water. And that gives us this right here. So that is an anti-Markovnikov addition of water. So we get this. And then you say after that we do, what do we do after that? PbR3. Okay, excellent. Excellent. PbR3. So that will transform the alcohol to an alkyl bromide. So we now get this. Okay, now what do we do now? Now we have formed our alkylating agent, right? So now we start with the malonate. Now we start with our malonate. Now we want to alkylate the malonate. Very good. You say ethoxide. Excellent. Very good. Very good. Very good. Okay, so now we say step 1. Okay, the ethoxide will deprotonate this alpha carbon here to form the Enolate anion. And then step 2, you add the alkylating agent, the one that we have just made. Keep in mind this is an SN2 reaction, okay, and that will give us this compound here. Okay, so now what do we do next? What do we do next? What do we do now? Keep in mind, this is where we want to go. Okay, oh, exactly. Now we do You guys say we now do hydrolysis. We now do hydrolysis, acid catalyte hydrolysis, and I would do this here, and then we get this. We get a beta dicarboxylic acid. And then we have this here. Okay, and then after that, you guys said we should do apply heat, and then okay, you apply heat, we lose this carbon dioxide. Okay, and this hydrogen here will come to this carbon right here. Okay, so therefore, and that is one of these hydrogen right here. Okay, so plus carbon dioxide. Okay, is there any question on this? Okay, so far so good, no question. Okay, let us go to question number 14. Okay, let me see here. If you have not talked to me today or talked to us today and your mic is working, can you pick up the mic and read this question for us?
Starting from cyclohexanone, write a synthetic scheme for cyclopentane carbonyl chloride.
Okay, very good, and thank you. That's Cynthia Jaffo. Very good. Okay, so now what they want us to do here, starting from cyclohexanone. So we need to know cyclohexanone, of course, the structure of cyclohexanone, which is this here. This is cyclohexanone, and then they wanted to give the synthetic scheme for cyclopentane carbonyl chloride. They are also testing your knowledge of nomenclature, so they want you to go to here. Cyclohexanones. Okay, I see. Now they want you to go to cyclopentane carbonyl. Okay, that is okay. Let us, because you are starting with cyclohexanone. This is actually a little bit more complex, but I think there was a mistake made here. This was supposed to be starting with cyclopenta. Okay, that's a mistake right there. So you are supposed to start with cyclopentanone, not cyclohexanone. So let us go ahead and correct that. Okay, so this is supposed to be here. Okay, but I am going to come back to this though. Supposing, okay, let us do this first, then I will come back to this, because we could actually go from cyclohexanone to this here. That is a very interesting question. Okay, so let us do here. Let us assume that the mistake was made, and this is cyclopentanone, and we are supposed to go to cyclopentane carbonyl chloride. So what do we do? Okay, in this case, we need to form a new carbon-carbon bond, right? We need to form a new carbon-carbon bond. So how do you do that? And then get to here. So could we? Yes, yes, Jaconda, you got the point. I'm coming back to that question. Yes, we could do Fibonacci. That's why I said it is a very interesting question. Yes, excellent. But let us assume that this is what we want to do. So how do you go from here to here? Wittig. Okay, we do Wittig. Wittig. Okay, so Wittig once again will give you this here. In other words, we are going to use this Wittig. Okay, then what do you do from there? Okay, after you form this here, what will be the next step? Okay, I'm waiting for your guidance here. What will be the next step? Go ahead. Okay, we form Wittig. Keep in mind, this is where we want to go. Okay. Hydroboration. Okay, very good. Hydroboration. Okay, and that gives us the anti-Markovnikov addition of water across the carbon-carbon double bond again, and we form a primary alcohol. Okay, so now what do we do now? Okay, exactly, very good. Chromic acid oxidation, because you want to form a carboxylic acid. Excellent, you guys are rolling tonight. Okay, okay, very good. So now you have this. Okay, then what do you do after that? Okay, thionyl chloride, excellent. Now you do thionyl chloride. Okay, so now you get this. So this is a very good question. Okay, and that is what they want us to make right here. Okay, now, okay, so that is one aspect of this question. That is one aspect of this question. Now, supposing, I'm assuming that you guys are writing most of this down. Can I erase this? If I can erase this, give me a happy face. I'm going to erase this. Okay, very good. Okay, supposing that this question, the way it was worded, is correct, just as Jaconda told us, he said we could use Favorsky. Why not use Favorsky? Okay. So it is a very interesting question. Supposing this is actually correct, which actually is a very good question. Here. So this has given me some idea for your exam. Okay, thank you, Jaconda. Okay, so now, supposing this is what they actually want us to do. Okay, so how do we do it? Okay, let us start with cyclohexanol. Okay, you say sodium hydroxide. Okay, okay, you say, okay, so you say we want to do this, right? But don't we need something else in there also? Okay, let us see here. Don't we need something else before we do the sodium hydroxide? Okay, think about Favorsky reaction. What do you need for Favorsky reaction? You need an, exactly, you need an alpha halo cycloketone. Okay, alpha halo cycloketone. Okay, to get the alpha halo cycloketone, you could do this. Bromine in acetic acid. In other words, you want to do the bromination of the alpha carbon here. You are using an enol, because you are using acid catalysis here. You are going to form an enol, and then the enol will eventually react with the bromine to form this here. Okay, so you do need the alpha halo cycloketone. Now, once you've done this, then what is the next step? What is the next step? Okay, now you form this compound. Exactly. Now you need an hydroxide, okay? You need hydroxide. Step 1, right? And then step 2, hydronium ion. And so that would therefore give you ring contraction. You are going to go from a 6-member ring to a 5-member ring, which is what we need. And in the process, you will be forming a carboxylic acid. Okay, so this process here, right here, from here to here, this is what we refer to as Favorsky reaction. Okay, which is what Jaconda gave us to use. Okay, now that you form this, what do you do now? Once you form this, what do you do now? Thionein chloride. Excellent. Now you then react this with thionein chloride, you get your acid chloride. Okay, do you guys follow this? If you follow all that, give me a happy face. Yes, very good, very good. Okay, now let us go to question number 10. Somebody said question number 10. Hopefully we will be able to get out of here by 9. So I think we are on target so far. Okay. Okay, if your mic is working and you have not spoken to us today, can you pick up the mic and read this question for us?
Consider 2-cyclohexanone. The gamma hydrogen is acidic. Briefly explain with the acid of resonance structures.
Okay. Okay, thank you. I'm very good. Okay, that's Ariana. Very good, Ariana Mango. Okay, so now what they want us to do here, say consider 2-cyclohexanone. The gamma hydrogen is acidic. Briefly explain with the aid of resonance structure. Okay, of course, they are also testing your knowledge of nomenclature here. So, where is the structure of 2-cyclohexanone? Is the structure here? This cyclohexanone, and since they say 2-cyclohexanone, that means you have a carbon-carbon double bond in the 2 positions, so that is right here. Okay, now let me ask you this question here. I am going to label this. This is carbon 1. Let's say this is carbon 1, carbon 2, carbon 3, carbon 4. Okay, let me just go this direction right here. Well, okay, that is fine. Carbon 5, carbon 6. Now, which of these carbon here is the gamma carbon? Just give me the number. Carbon number 4, exactly. That is correct. This is that is correct. Gamma carbon. This is alpha. These are the Greek symbols, and this is beta. The number 3 carbon is beta. That is relative to the carbonyl. Okay, relative to the carbonyl. That is beta. And relative to the carbonyl, the carbon number 4 is gamma. Okay, so now once we know that, okay, let me go ahead and erase this. We know the gamma carbon, and therefore we know the gamma hydrogen. because attached to the gamma carbon are the gamma hydrogens. So we have these hydrogens here. The question they are asking is, these hydrogens are acidic. Why are they acidic? And then give an explanation. Okay, so let us see here. Let us assume that we have hydroxide here. And this hydroxide will come and abstract this hydrogen here to form a negatively charged carbon atom. So this comes here to form a carbon ion. Okay, so what do we get? We get this. Negatively charged. The question is, why is this hydrogen, why is this acidic? The answer to that is because of the stability of this conjugate base due to resonance stabilization, because we could move this electron here to here. Keep in mind, this is an sp2 hybridized carbon, sp2 hybridized carbon, sp2 hybridized carbon. So we could delocalize that electron. This goes here. This goes here, right? So we form. An enolate anion. So we form an enolate anion. So the answer to this is the anion that is formed as a result of the conjugate base of this is resonance stabilized. It's stabilized by resonance. So you form this enolate anion here. This is hydrogen. So we form an enolate anion, and we know that enolate anion are stable due to resonance with the carbonyl. So we could have additional resonance. In this case, this goes to here. Now this pi electron comes to here. So this conjugate base, therefore, is stabilized by a series of resonance structures, and one of them is this one also, involving the carbonyl of involving the oxygen of the carbonyl. Okay, so we have this. So now we have this, we have this, and then we have this right here. Okay, so all of these resonance structures here, three of them, they are stabilizing this conjugate base, and that is the answer to the question. The question they ask is, okay, briefly explain with the aid of resonance. Okay, all you need to do here, your explanation will simply say that as a result of resonance stabilization, the conjugate base is stable. Okay, that is the answer you give. And the reason why it is acidic is because it is resonance stabilized, this conjugate base. Okay, do you follow that? Okay, somebody asked me a question. How do you figure out alpha, beta, gamma when it's not? Okay, if it is not a cyclic molecule. Okay, good question, good question. Okay, if it is not a cyclic molecule, it is the same relationship. Okay, the question that Christopher is asking, how do you figure out alpha, beta, gamma if it is not a cyclic molecule? So that's a good question. So just want to change my color of my pen. Supposing we have this. Okay, relative to this here, relative to this here, this would be 1. Okay, if this is 1, let us assume that this is 1. Let's say this carbon is 1, okay? And then we say this is 2. We say this is 3. We say this is 4. So it is the same relationship. So the carbon number 2, which is attached to the carbonyl, that is the alpha carbon. So this is alpha carbon. Therefore, the hydrogen attached to it will be alpha hydrogen. And therefore, the relative to this carbonyl, the number 3 carbon here is beta carbon. Therefore, the hydrogen will be beta hydrogen, and also therefore this also will be gamma carbon, and the hydrogen will be gamma hydrogen. Also, if you take a look at this also, this methyl carbon here is also an alpha carbon, because it has a 1-2 relationship to the carbonyl. So therefore, these 3 hydrogen here are also alpha hydrogen. Is that clear? Okay. Okay, so let us now go to, I think that was question number 10. Let us go to question number 9. Question number 9. Okay. Okay, if your mic is working and you have not spoken to us today, can you go ahead and read this question for us? Okay, so, okay, well, let me go back to the beginning then. Natalia, go ahead and read this question for us.
Arrange the following compounds in the order of increasing acidity: acetic acid, 3-chloroacetic acid, monochloroacetic acid, and dichloroacetic acid, and briefly explain your answer.
Okay, very good, and thank you. Okay, this question, once again, is simply testing your knowledge of acidity. Okay, so what molecule do we have? We have trichloroacetic acid. Let me write the molecules here. Trichloroacetic acid. This is C. Okay, carbon with 3 chlorine atom, acetic acid. That is trichloroacetic acid. Then you have monochloroacetic acid, and that would be this here, CH2 and 1 chlorine, and then you have the carboxyl group. That is the monochlorocarboxylic acetic acid. Then you have the dichloroacetic acid. Dichloro, that means you have this. Two chlorine atom. Then you have, so you have that. And finally, we have acetic acid right here. Acetic acid, and that would be this here. Okay, so what they want us to do here is to arrange this in the order of acidity. Let us say most acidic. Let us say most acidic. To least acidic. Okay, what I want you guys to do here, I am going to put labels on this. Let me put numbers on this. Let's call this 1. Let us call this 2, just based on the way we've written it here. Let us call this 3. Let us call this 4. Okay. Of all these 4 acids, which is the most acidic? Just give me the number. Most acidic. 2. Very good. You said 2. Okay. Okay, I would take it for now, but I'll come back to ask you why. Which is the next? In other words, you say the trichloroacidic acid is the most acidic. You say number 4, so okay, more acidic than number 4. Okay, I will say more than number 4. Okay, which is next after that? You say number 3. Okay, more acidic than number 3. And which is the least acidic? Number 1. Okay. Okay, so this is acetic acid. By the way, you guys are correct. You guys are correct. And then the next one is 3. This is this one here, monochloro. You guys are correct. And then you say number 4, dichloro. And then finally you say the most acidic is the trichloro. Okay, let me ask you this. This is correct. Okay, why did you pick this order? Why did you pick this order? This is correct. Why did you pick this order? Because of electron withdrawing, exactly. Okay, because of what we call inductive effect. Inductive effect as a result of electron withdrawing. As a result of electron withdrawing. Ability as a result of electron withdrawing ability. Okay, very good. Now, keep in mind what we did, I said before about acidity of organic molecule. We said the acidity is based on the stability of the conjugate base. In this case, the conjugate base here, for this here, the conjugate base will be this. Let me go ahead and write this out better. You guys are correct, but I just want to give a little bit explanation for the benefit of those who will be watching this video, and then some of you who may not completely understand the process. Okay, so you have this. Okay, so this is the conjugate base of this, and indeed for all of them, that is what the conjugate base will look like. And if you look at the electronegativity here, chlorine relative to carbon is very electronegative. So what you are looking at here, this will be pulling electrons away from this part of the molecule. Think of this. All of this chlorine here will be pulling electron away from this part of the molecule, and that is what we refer to as inductive effect. Okay, once you form the conjugate base, the chlorine atom here will be pulling electrons to this side of the molecule, thereby helping to stabilize the conjugate base. And the more chlorine atom you have, the greater the inductive effect. You have 2 chlorine here, you have 1 chlorine here, and you have no chlorine here. Okay, is that clear to all of you? Okay, very good. Okay, so let us do the last one. I think it's almost 9 o'clock. Let us do one more question. Number 8. You guys say we should do number 8, unless you want us to do any additional question. Okay. Jaconda, can you go ahead and read this for us?
Reaction of lithium aluminum hydride with an ester followed by acidification gives a primary alcohol. Write the mechanism using a generic ester. Identify the types of reactions that are involved in the mechanism.
Okay, very good, and thank you. Okay, this question here. This is what I call a classic nucleophilic acid substitution type reaction. Nucleophilic acyl substitution type reaction. Okay, and it also actually involves two types of mechanism. One is the nucleophilic acid substitution. The other is nucleophilic addition to carbonyl. So we have two mechanisms going on here. One, this is one, then the other would be nucleophilic addition to carbonyl. Okay, so let us take a look at it. Now, it is a good question because it does help you to understand the other types of nucleophilic acid substitution reaction. The difference here is that the reagent is just different. Let us start with this. Supposing we start with this ester. Okay, let us say we start with this ester. Okay, I'm going to get rid of this. Keep in mind that we have two reaction mechanisms involved here. Remember, we told you LAH. What does LAH give you? What does it give you? What does hydride? Exactly. Okay, folks. Think of this hydride as a nucleophile. Okay. Think of it as a nucleophile just as much as you would think of this amino group as a nucleophile. There is no difference between them in the way they are going to react. Just as sometimes you may want to think of water as a nucleophile, it is the same type of concept that is involved here. Okay, having said that, what do we have? So we have the hydride coming here. Let me use a different color pen. Use green here. So the hydride coming in, acting as a nucleophile. Now, what do you think it's going to do? What is the hydride going to do? Anybody has an idea? What will it do? What will the hydride do as a nucleophile? You have carbonyl, attack the carbonyl carbon. Excellent. Excellent. So what it does, attacks the carbonyl carbon. Okay? And then, of course, this electron goes to oxygen. Pi electron goes to oxygen. And that is, so now you have this. This is negatively charged. Don't forget that this was here before. Okay? Now this hydrogen here is here right now. And of course you have the methoxy group is here. Okay? So now what happens next? What happens next? Double bond will reform. Carbonyl will reform. Exactly. Okay? Carbonyl will reform. And when it does, this carbon here can only have 4 bonds, so something has got to give, and that something will be the loss of this methoxide. Exactly, will break away. Okay, and this is why I call this a classic nucleophilic acid substitution. Because what have we done here? So far, this is the nucleophilic acid substitution right now. And that is a classic nucleophilic acid substitution. So why do we say it is nucleophilic acid substitution? Because what happens, we replace the hydride, we replace the hydroxide with the hydride. In other words, the hydride here displaces the methoxide, okay? And it is a substitution reaction. So you see the hydride comes in, displacing this here, so you form this. So that's why I say Well, the first reaction is a nucleophilic. Acyl substitution. Okay, so now do not just think of this as just an hydride. It could, like I said, it could be ammonia. It could be water. Okay? It could be any nucleophile. Okay, now what happens after that? Because keep in mind that this actually gives us a primary alcohol. Okay, it gives us a primary alcohol. So, what happens after that? Another hydride comes in. Now the hydride is now going to do a nucleophilic addition. Remember I told you there are two processes going on here. So the hydride comes in. Now it's going to do a nucleophilic addition to carbonyl. This goes here, just like before. Okay? And therefore, what do we have? We have this. Now we have two hydrides. Now see what has happened here. We now form this alkoxide here. Now, it is not easy for this alkoxide to come back and reform a carbonyl because the hydride is not a good leaving group. See, the hydride is not a good leaving group. Therefore, because it is not a good leaving group, this alkoxide will simply just stay where it is until you add water to it, until you add dilute acid. And then it simply picks up the proton from the dilute acid. And that is why when you do the reaction with LAH, you follow it up with that dilute acid. And therefore you form your primary alcohol. And that is your primary alcohol. And that is what they told you here. Okay, and this is the complete mechanism. So the second part of this here, this is nucleophilic addition. The second part of this, from here, okay, to here, that is nucleophilic addition. I told you there are two processes. That is nucleophilic addition to carbonyl. Okay, now if I really want to make this a complete process, this here, this last part here, going from here to here, that is an acid-base reaction. So we could actually say there are three processes going on here. This is an acid-base reaction. Okay, and I think at this point, do you guys have any questions? I think it is 9:04, so we have spent just a little over 1 hour. If you guys do not have any question, I think this would be a nice place to stop our session today. Oh, somebody said we should do number 12. Okay. Okay, let us see. Let us do number 12. Okay, somebody say I agree. Okay, good. Let's do number 12. Okay, number 12. Okay. Kiera, can you go ahead and read this for us? Okay, I don't think Kiera is ready.
Hello for amino, so I don't know how to say that, is used in the treatment of tuberculosis. Provide a synthetic scheme starting with 4-nitrosilicic acid.
Okay, very good, and thank you. Okay, so what they have here, phenyl 4-aminosalicylate, this here, phenyl 4-aminosalicylate, okay, which is this here. It's used in the treatment of tuberculosis, okay, and of course, they say that this compound can be synthesized starting from here. So what they want you to do now is to provide the synthetic scheme going from here to here. Okay, so let us see here. How do we do this? Let us do our analysis. Okay, what is going on here? Can you guys hear me? If you can hear me, okay, good. Let me go out. I think I just lost my internet. I will come back to you. Give me 1 minute, okay? Don't leave. Just stay right there. Okay, can you guys hear me now? Okay, very good. Okay, I lost my internet. Anyway, okay, so let us finish this question and then we call it a day. So what we have here, so we want to go from this molecule here, just do our analysis here. All that is happening here, we need to transform this carboxyl to an ester. That is all that is happening. So therefore, what do we need to do? How do you make an ester from a carboxylic acid? How do you make an exactly? Very good. Thionyl chloride. Very good. Excellent. Do thionyl chloride. And then you have this here. You form your acid chloride. And then what do you do after that? What do you do after? Okay, then use the phenol, react with the phenol. Excellent. Really, it's a very simple process to make a very valuable pharmaceutical drug. It is a very simple process. And so this is another, okay, the reaction of this here, the phenol with this, what type of mechanism is it? Okay, remember what we did in the previous reaction. No. SN2 reaction only on sp3. This is an sp2 carbon, not SN2. No. Remember what we did in the last section. The nucleophilic acid substitution reaction. Excellent. So this is another example of a nucleophilic acid substitution reaction. Okay? Keep in mind, SN2 reaction will not take place on an sp2 carbon. Keep that in mind. SN2 reaction only takes place on sp3 carbon atom that is primary or secondary. Okay? Okay, and that is our product, which is this here. Okay, so this is another example of nucleophilic acyl substitution reaction. Okay, so what have we done here? This here, the phenol oxygen here has replaced the chlorine, so you end up getting HCl. Okay. Okay, the nitro group changed. Wait a minute. The nitro group did not change. Let me see here. No, the nitro group did not. Oh, I'm sorry about that. Yes. The nitro group now changed. Yes. So one more step. Folks, yeah, I was trying to jump the gun. There is one more step to go. The nitro group becomes amino. Thank you. Who said that? Jaconda. Very good. So now, what do we need to do that? To transform a nitro to an amino, what do we need to do? Okay, hydrogen, exactly. You do hydrogenation, hydrogen in the presence of a catalyst. Now, what other reagent can we use? Or you could use iron, okay, in the presence of dilute acid. Okay, you could also do that, okay? So that would transform an amino group, a nitro group to an amino group right here. Okay, so at this point, folks, we have come to the end of our session today. And for those of you who want to stay behind for another 5 minutes, I will stay around for 5 more minutes if you want to ask additional questions. And for those of you who are leaving right away, enjoy the rest of your evening, and I will see you on Tuesday.